Hello everyone, welcome back to the Control System Engineering lecture. In this lecture, we are going to study about the state space analysis. Till now, we have completed the transfer function analysis and design of a controller using the transfer function, which are the part of the traditional control theory. Now we are moving forward to the modern control theory, and the state space analysis is a part of a modern control theory. So let's start with the difference between these two design methods. The transfer function method have few disadvantages. Like the initial condition in transfer function is always assumed to be 0. It is not possible to consider the initial condition in the case of transfer function design. Transfer function design is all the frequency domain design. There are a Laplace transform there for defining a transfer function. All controller is actually designed with the specification of the frequency domain like phase margin and gain margin. Application of the transfer function is only applicable to the single input, single output system and the linear LTI system. However, the state space analysis has few advantages over the transfer function design, like non-zero initial condition can be considered in the state space analysis, time domain model and design. It is a time domain design. The state space analysis can also be applicable for the nonlinear system, multi-input, multi-output system, and the time varying system. So state space analysis is also applicable for any kind of physical system that you have. Like if you have biomedical representation, then you can define a complete biomedical system in the state space analysis. For understanding a state space design, let's consider an example of a DC motor control, armature control DC motor. There are two equations in the armature control DC motor equation. One is your mechanical part and second is your electrical part. So let's say we are controlling the speed of a DC motor, which is represented by angular velocity omega, and the input of the system is V. So we can define that output of the system by Y, which is the omega, and input of the system is V by the U. So U and Y is actually the nomenclature for the input and the output of the system. So let's say we actually drive the motor required a current to generate a particular speed. So the I is actually defined by another value. Let's take a few nomenclature like omega equals to x1 and I equals to x2. There are two variables in the equation, and we already defined that v is equals to u in this case. So x1 and x2 are called the states of the equation, which are responsible for driving output of the system. So in this case, we have choose the state of the equation is current and the velocity. However, it is not restricted to use these only state equation. If you want to use different state, then you can use a different state. So if you represent your state differential equation in terms of x1 and x2, so we will have this kind of x1 and x2, and this equation can be represented in form of a matrix. So the vector x1, x2 are called the state vector. X1 and x2 are independently called the state variables and states of the system, represents the states of the system. U is the input of the system, and the matrix associated with the U, which is 0 and minus 1 by L, are the control matrix, input matrix. Matrix come together with the x1 and x2 are called the state matrix, and output equation y is equals to 1, 0, x1 and x2, since we have defined y equals to omega, and omega is nothing but we have defined with the x1, so this y can be represented in this form. So this matrix 1, 0 is called the output matrix of the system. So this is the typical representation of your state space analysis design of any system can be modeled in this form, in this matrix form. So what are the definitions? The state of dynamic system is the smallest set of variables such that the knowledge of these variables at t equals to t0 together with the knowledge of the input for the t greater than t0 completely determine the behavior of the system for any time t greater than equals to t0. State variable, these are the defining variable like x1, x2 as we have already explained. This is called the state variable. And combination of the state variable are called the state vector like this. The state space equation, however, the equation that we have in the form of states are called the state space equation. The definition of the state space equation like this. The n-dimensional space whose coordinate axis consists of x1 axis, x2 axis, xn axis, where x1, x2, x3, and so on xn are the state variable called the state space. Any point can be represented by a point in the space. The standard form of a LTI system in a state space is actually this, where we have a differential equation of state x dot equals to ax plus but, where A is a state matrix, B input matrix, C output matrix, D is a feed forward matrix, and the Y is equals to cxt plus but. The block diagram representation of the state space equation is like this. There are different state space equations, like for an example, a time varying system, state space equation, the constant matrix A, B, C, and D in time varying case will be the function of the time. So it is represented by AT, BT, CT, and DT. Now in this case, these metrics are not constant, will depend upon the time. Similarly, in case of discrete state space equation, the differential equation can be represented by xk plus 1. This is the future next value, and xk is the present value, like this. The nonlinear equation will nonlinear state space equation can have any formula, not necessarily in the form of ax plus but. However, it may have any formula like x1 square plus x2 square plus x1 x2 sine x1 x2, any function it can have of state, a control input u, and function of time. So I have represented the nonlinear state space equation in the form of x1t is equals to function of x, u, and t. Similarly, y is may also be the function of x, u, and t. Now comes to the point correlation between the transfer function design and space analysis. Let's say if we have a state space equation like this, x dot t equals to axt plus but and yt equals to cxt plus dut. Now if we take a Laplace transform, now since we are defining this state space equation into a transfer function design, so we will consider initial condition will be equals to 0. So x0 equals to 0 we will consider. So the Laplace transform of this equation can be represented like this. So if we solve this equation, we will have xs equals to si minus a inverse, where I is the identity matrix since we are dealing with the matrices here. So we will also consider S into Y is an identity matrix in this case. So Si minus A inverse B US, where B is your input matrix and U is your input of the system. The transfer function can be defined if we find out the output upon input. Output is the Y. So if we substitute the value of XS into the equation YS, then we will have YS equals to this formula, and the transfer function will be ys upon us equals to c multiplied by si minus a inverse b plus t. Let's take an example of this equation. Let's consider the state space equation. If you want to calculate the transfer function in this case, then you can simply substitute the value of c, which is 1 0, S into I, identity matrix. The identity matrix dimension will be the same as the dimension of the A matrix, minus A inverse of that matrix, and 0, 1 upon M, which is the B matrix, plus D. D is 0 in this case. If you solve this equation, you will have the given transfer function. Please also note that in the characteristic equation of this particular state space model can be calculated with the given formula, which is the Si minus A inverse determinant of Si minus A inverse. So please do these following problems with yourself to have a practice on this. So these are the two problems for you. Now we will do the transfer function to the state space domain. If you have any transfer function in the given form, then you can define your uh, transfer function into any state space equation. There are infinite possibilities of the state space equation. However, in control system, we generally deals with the four kind of different state space forms. So in this form, we have a controllable canonical form. Let's say if you have a G is a transfer function in this form, which is ys output upon input us. If you represent the ys upon us in the form of ys upon xs dot xs upon us, where x represent the state Laplace transform. So we can define these two equations in this form. Let's say this have ys upon xs will equals to the this value and xs upon us equals to this value. If you take uh, inverse Laplace transform of these equation, you will find out a differential equation in this case, which are given in this form. And if you represent the states of the states in this case, then let's say we have a state x1 equals to x. We have defining the first state x1 equals to x. Then second state x2 can be defined x1 dot, x3 can be defined x2 dot, and so on. And the last state x n and derivative nth derivative of xn dot equals to, we will have u minus the whole an x1 minus an minus 1 x1 and so on minus a1 xn minus 1. So the xn dot can be represented like that. So if we represent these whole equation x1 to the xn dot equation into a matrix form, then we will have a matrix in this form. X1 dot equals to 0, 1, 0, 0 because x1 dot equals to x2. So we take 0, 1, 0, 0, 0. X2 dot equals to x3. So therefore we take second row will be 0, 0, 1, all 0. Similarly, the last value will be minus an minus 1 minus an minus 2 and so on a1. Because in the last equation, if we observe, we will have x1 dot equals to u minus the all static equation with the coefficients of a into a1. Similarly, since the u is coming into only the last equation, so the u all values in the input matrix, control input matrix will be 0 except the last value will be equals to 1. Similarly, if you substitute the value of x1, x2 and x3 in the state equation y, you will end up with the following formula of the y, which is the bn minus an b0, bn minus 1 minus an minus b0 and so on. And the D matrix will be in this case will be b0 into u. Now second, the controllable canonical form can be represented like this. If I summarize this form, so G, if we have a transfer function G, then A matrix will be equals to like this, B, D and C like this. Similarly, we have second kind of canonical form. The second type of representation is observable canonical form. There is a duality behavior in the controllable canonical form and observable canonical form. If you notice that A matrix is the same as the controllable canonical form. However, in this case, the A matrix is the transpose of the previous matrix. So we will have in observable canonical form, the A matrix will be transpose of the controllable canonical form. Also in this case, the C matrix is equals to 0, 0, 1, which was the previously was a B matrix. And this B matrix in this case is equals to Bn minus An minus B0, which was the C matrix in the controllable canonical form. So if I have to compare these two form, the A matrix is a transpose of the previous matrix. C and B matrix are exchanged in this case. So these are the formula for the observable canonical form. The diagonal canonical form. The diagonal canonical form generally represent your poles of the system into a diagonal of our state matrix. For a diagonal canonical form, we have to take a partial fraction of your transfer function in the given form b0 plus c1 S plus P1 and so on. The P1, all poles of your system will come inside the diagonal form of your A matrix. And similarly, the C matrix will be the numerator of your all partial fraction coefficients C1, C2, and C3. And the B matrix will be the 1, 1, all one matrix into that form. So this is called the diagonal canonical form. That called Jordan canonical form. Let's say we have a three poles of P1 at the same location and S equals to minus P1 three times. So in that case, we represent a matrix in this particular form. The all three pole P1 and P2 represented posed into a diagonal form. However, it will come together with the 1 in the upper triangular part of your P1 and P2 case. Okay. Similarly, in case of B matrix, only all values before the last pole, which is the last pole. In this case, we have a three poles, same location, P1. So we will represent your three location of pole in B matrix is 0, 0, 1. If it has four locations, so B matrix will be the 0, 0, 0, 1. And C and D matrix will be the same as the diagonal matrix. So this is called the Jordan canonical form. Let's consider this example. I will leave that example for you to do the practice. Use the given formula of controllable canonical form, observable canonical form, and diagonal canonical form, and find out the state space representation of the matrix transfer function into the given form.